So here is the first problem. There is given a thin ring with radius a with a charge q placed on the height h above plane z equals 0, which is grounded and conductive. So first, it needs to describe the charges which affect electric field. So the charges which affect electric field will be on the ring, and these charges will mirror on the charging plane. So there will be a surface charge distribution on the grounded plane, mirror charge. And then second, motivate with some, meaning what for potential is under the charged plane. So under the charged plane, there is a constant potential, but electric field is 0. So let's see the figure. So on this figure is presented the charged plane and the charge q on the ring. And using the image method, I introduced here imaginary charge minus q, which will be the charge on this grounded plane, conductive plane. So it's a mirror charge. This charge doesn't exist, so there is no charge under the plane, just the mirror charge on the on the plane. So for the first case, electric field is in the, so let's say it's z axis, here is the 0. So in z positive, there is some electric field, not equal to 0. At the positive axis, and underneath, under the plane, there is no charges and no electric field, so that the charges on conductive plane will distribute in the way to shield any electric field which could be, so all the electric field is above the plane. And the second question was about potential. So if electric field is 0, then potential is constant from the formula. So the potential is integration, and in this case we will have a constant potential under the plane. And so that's for the case under the plane. And then the third question is to find the potential on the symmetry axis above the grounding plane. So the potential above the grounding plane will be a sum of potential on this plane and on the ring. Total potential is from Q plus minus Q. And now we need to define each equation to find potential using the field pages given here. So first, the charge density in the volume, and let's define the x and x prime. So let's say this is let's use a cylindrical system of coordinates. So let's say it's a z-axis up, and then the radius is in radial direction, so we can describe x and x prime for the charge q positive. So the charge q x is some z direction somewhere here, any point along along symmetry axis, and then x prime is it's elevated on the h, and then it has radius a in r direction, so we describe all these points, right? And now this will be equal to for the positive q. So what will be different for the negative q? It will be on the distance minus h. So for the negative q, r, so this part is r of q plus, r would be z plus h. This way. Yes, and of course we need here absolute value. So the absolute value would be for the q minus and for the q plus. Those, and then we plug it in this equation here. Okay, when it's squared, here is a plus and plus. And then for the charge density in the ring, it will be Q divided by 2PA. So the charge in the ring, and for the dV, it's the volume is actually replaced with K d phi, and then the integration becomes d phi. This is Q. A and A are gone, and then here 2 pi and R. So now for the both rings, so since it's d phi along the circle, 2 pi will be gone, and then only R is left. minus because of one distance is for the Q charge and another radius is for the minus Q charge. So that's the answer for the potential above the grounded plane.